Network failures happen. If you follow any amount of news, you'll regularly come across stories about how network reliability issues impact different applications. Of course, if you operate your applications on Kubernetes, you've likely had first-hand experience here as well. Developers and SREs can frequently find themselves in a blame game with the network. Your application is behaving erratically, and you don't know if it's a problem with your code or something in the underlying network. Maybe a slowly dying switch is introducing packet loss and pulling up your P95 latency. And it has a small enough blast radius that your cloud provider may never even post about it on their status page. The last thing you want to do is page half the team to debug a problem that really exists in a cloud provider. You need better visibility into your Kubernetes environment. Network monitoring today is a bit of a loaded term with a long history. It's primarily been associated with on-premise tools built for device configuration, hardware health, connectivity and capacity metrics, and occasional packet capture. As we start thinking about microservice and cloud environments, these tools really start to lose their utility. Cloud providers operate opaque software-defined networks, but they can still break and wreak havoc on an application. IP addresses and other packet-based data is often ephemeral, and it's hard to map to the actual containers you operate. And packet captures may be difficult to execute, and traffic flows may be metered and drive up cost within your cloud provider. The reality is there's a different class of use cases that emerge as we think about network telemetry in a Kubernetes environment. So what are some of these use cases that emerge? Well, first, network telemetry can give you an up-to-date, complete view of all service dependencies, so you can deploy services with confidence. If you move something or change something, you should know all the related services that could be impacted. And if someone new joins your on-call rotation, they can quickly orient themselves and understand the entire system. Second, you must be able to quickly separate network outages from application issues using service-oriented data, so you can direct troubleshooting to the right places quickly. This could mean you'll move containers off troubled cloud instances, or call in application developers with the confidence to say the network is really behaving normally. You need to end the blame game between the application and the network. Finally, you'll be able to measure and optimize your cloud networking costs. As Kubernetes services scale and communicate across availability zones, it can be difficult to connect cloud transfer costs with the actual services driving those costs. By gaining visibility into how services communicate across availability zones, you can optimize traffic patterns and reduce surprise transfer cost bills. So what do you need in order to achieve this level of visibility? The first source of information is sockets. This is similar to the flow data you're used to: source and destination IP addresses, port numbers, bytes sent, packet drops, round trip times. But it's possible to get deeper visibility into application behavior by looking at the payloads. For example, from HTTP, you can understand if it's a GET or a POST, the endpoint that was queried, the response code, so on. But all this really has IP addresses. To really make it useful, this data needs to be joined with information about what service is running. What's the service's version? Where is it running? The metadata that Kubernetes has becomes really critical. And actually, by stitching all this data together, now you can analyze data in a holistic way, create service maps, surface failure, and really support deep drill downs into application relevant data. Now, you could get all this data from the Linux command line. Let me show you how, but then I'm going to explain why you probably don't want to. Let's say in Kubernetes, container A wants to reach a service X, which is served by container B. Kubernetes is going to create a VIP, a virtual IP for service X. So A will open a socket and connect to X's IP address. IP tables will actually perform a NAT translation. It'll modify the packet that's addressed A to X to A to B. And B will then see the traffic as if it's coming directly from A. Now, how would we get visibility into this in the command line? Well, first from the Kube API, we can actually get information about the services and their associated IP addresses. We can next use the SS tool for socket stats. This will tell you that A is sending data to X and how many bytes actually get sent. Finally, we can actually use contract command to look at connection tracking. And we can get information about the translation from A to X and how that's translated from A to B. While it's possible to get this kind of network telemetry from the command line, it comes with some major disadvantages. Overhead is pretty high because we're running a process every time we want to get just one piece of this data. And these tools may have to iterate over every socket in the system, which can be a very expensive operation. It's also lossy since the tools might run at some regular interval and they may miss sockets that are short-lived. So we won't even be getting a complete view of the data. And finally, these CLI tools are actually limited in what the kernel exposes. They can't actually see into the kernel data structures and get the complete view of the system. This is where eBPF comes in. eBPF allows developers to run programs inside the operating system when different kernel events happen. For networking, you could run eBPF code when TCP handshake of a new connection is complete, or when TCP receives an acknowledgement for a packet. It provides an efficient way to get a stream of notifications about important events. And the BPF system call has been part of the kernel since 2014, so it's very widespread in all the major distributions. Big advantage of using eBPF for network observability is the kernel actually runs the code, so there's no changes required to the application. The kernel also contains a compiler and verifier for eBPF. So one thing this can do is actually compile to machine code, yielding a highly efficient program. The verifier will actually statically analyze the code to make sure it's free of invalid memory addresses. And for observability, eBPF can actually run in a read-only mode, so it's prevented from making changes to the underlying kernel and causing any damage. The end result is that eBPF really can give you the performance of a kernel module without any of the stability and safety issues. And it turns out to be one of the best ways of getting network visibility into your Kubernetes environment. Now at Splunk, we're big believers in the power of eBPF for network visibility. We're both contributing to this in the open source community and building it into our observability products. As one of the largest contributors of OpenTelemetry, we've donated a set of agents capable of collecting and aggregating eBPF-based network telemetry in Kubernetes environments. This is available today, and we're excited to be working with the OTel community to advance it further. Thanks a lot for your attention and for learning more about network telemetry and Kubernetes environments and eBPF.